So welcome to Math 310 Introduction to Modern Algebra. And what we're going to do today is we're going to review some material from previous classes that will be showing up throughout the semester. Just making sure everybody's able to see my screen. Is at least one person able to see my screen? Okay, perfect. Okay.
Yes.
Okay, so the question was to review combinatorics. And so this is extremely important for counting. So we define 0 factorial to be 1, and n factorial is n times n minus 1 factorial if n greater than or equal to 1 is a positive integer. And it has a meaning. N factorial is the number of ways to order n objects. So order matters. This function is growing very rapidly, and it's a fun game to try to figure out just how fast is it growing. Now, if you've ever served in a club, hopefully your club has more people than officers, which means unfortunately you have a contested election and sometimes people go home feeling sad. So let's say we want to choose, 3 people from 8 to be officers, but all offices are different. So I believe Vice President George Bush years ago defined the vice presidency as you die, I fly. That the vice presidency was not that big of a role compared to the president. And so the question is, how many ways can you do this? Well, a lot of times people like to do it with boxes. How many options do we have for the first box if we're choosing someone from 8 people? So somebody want to speak up? So how many choices do we have for the first box?
8.
8. And how many for the second?
7.
7. So we're choosing 3 people. We can't have the same person serve as president and vice president. Now, there are times in war where somebody might wear multiple hats. There might be the prime minister and the secretary of defense. But typically, in a situation like this, we want distinct people. And then we would have 6 people here. So the answer is 8 times 7 times 6. But we're going to write this in a more illuminating manner. So one of the things you learn how to do in math is to do nothing. There's 2 ways to do nothing. You can multiply by 1, you can add 0. So when I have something like this is coming right after discussing factorials. So I probably want to be thinking about factorials. 876, that looks like a factorial, but it's missing a little bit. So let's multiply by 5 factorial. Now it's a factorial. The problem is you can't just multiply by 5 factorial, but we can if we also divide by 5 factorial. And when we do that, we now get 8 factorial over 5 factorial. And sometimes you might have seen this written as, I think it's 8p3. Does that look familiar from anybody from high school? Yeah. This is 8 factorial over 8 minus 3 factorial. It's the number of permutations. So if we know the factorial function, we can calculate something like this. If we want k from n when order matters, that is going to be n factorial over n minus k factorial. And this is coming from, let me just move this over to get a little bit more of them. And this is coming from n minus 1. And if we're choosing k people, we go down to n minus k plus 1. because we really start off with n minus 0. And then we're multiplying by n minus k factorial over n minus k factorial. So this is the number of ways to choose k people from n when order matters. So we just proved the number of ways to choose k from n when order matters is n factorial divided by n minus k factorial, and that's sometimes written np n minus k. And implicit is this is we're assuming n greater than or equal to k non-negative integers. You always want to be careful about where can you use a formula. What if order doesn't matter? Maybe we're forming representatives, or maybe we're just putting people on a committee. Well, let's take 4 people, say Alan, Barbara, Charlie, and Dan, and we'll just call it A, B, C, D. And we want to do a group of 3. Well, first we could do it as order matters. We could do, A, B, C, A, B, D, A, C, D. That should be all the ways of having A as the first element, right? Then we could have B as the first element. Sorry. Right. And how could we do with B as the first element? We could do, B, C, D. Could we have anything where C is the first one? Where C is the lowest named person in the group? Or are these the only possibilities? So I'm trying to list them by listing them with the lowest named person first, followed by the second lowest, followed by the third lowest. So when I do it like this, this is called a canonical way to go about this. This is a way that's hopefully going to guarantee I'm not going to forget anybody. So do we agree that these are the only possibilities? So this is group of 3. And order does not matter. But now let's try to list all the ways when order matters. If I give you ABC, I could have ABC. What else could I do? I could do ACB. I could do BAC. I could do BCA. I could do CAB. I could do CBA. And what we see is if I give you 3 elements, there are 3 factorial ways to order them. And similarly, there'll be 3 factorial ways to order each of the next. What does 3 factorial equal?
6.
6. Okay, so we have 6 ways to choose 3 people when order matters. If I tell you which 3 people, right? So if I tell you the 3 people are A, B, C, I can order it 6 different ways. Let's calculate what's going on. If I give you n equals 4 and k equals 3, then 4p3 is going to be 4 factorial over 4 minus 3 factorial. That's 4 factorial over 1 factorial. That's 24. So there are 24 ways to choose 3 people from 4 when order matters. So 24 ways to choose 3 from 4 if order matters. But what we see is for each choice of 3 people, when order doesn't matter, there's 3 factorial or 6 ways to order them. So another way of looking at this is I have 24 ways to choose 3 people from 4, but I can break these up into groups of 6. And each of those groups of 6 will have the same people, just in a different order. So if order doesn't matter, it is 24 over 3 factorial, which is 24 over 6, which is 4. So there's 4 ways when order doesn't matter. So we can view this as 4p3 over 3 factorial, or 4 factorial over 4 minus 3 factorial divided by 3 factorial, which is 4 factorial over 3 factorial, 4 minus 3 factorial. Or this is the n factorial over k factorial, n minus k factorial. What we're really doing is, if we know how many ways there are to choose people when order matters, we're removing the ordering. So if npk is the number of ways to choose k from n when order matters, we remove the ordering by dividing by k factorial. And we call this nck, or n choose k. We write it as nk with parentheses like this. And this equals n factorial over k factorial, n minus k factorial, when n and k are non-negative integers. So this is one of the most important basic combinatorial objects. And it comes from, you're just starting off with the factorial function, then we talk about how many ways are there to order things, and then we go from that to, well, we did order, and now let's remove the order. So any questions on what we've done so far? So far, so good? Okay, so now the connections to Pascal's triangle. And so we go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And each number is the sum of the 2 numbers above it. And if you want to extend that to stuff over here, you could imagine we have all these zeros as well. So 1 would be, this one over here would be 0 plus 1. And this one over here, and so on and so on. It turns out that one of the reasons this is so useful is I can view this as x plus y to the 0. I can view this as the expansion coming out from x plus y to the first. And this x plus y to the second, which is going to be 1x squared plus 2xy plus y squared plus 1y squared. Let me not try to compress this. Let me write it out carefully. So this would be x squared, xy, y squared. And the coefficients would be 1, 2, and 1. And what you can see is the coefficients when we expand x plus y to the n are coming from the nth row of Pascal's triangle. So if you want to think about this connection, so n choose k and Pascal. If I give you x plus y to the n, this is going to be the sum of some coefficients a and k, x to the k, y to the n minus k. K goes from either 0 to n or n to 0. And if you think about it, when I expand out x plus y to the n, everything I get, I have some number of x's, some number of y's. We need the power of x's and the power of y's to add up to n. So if I have k x's, I must have n minus k y's. Everybody comfortable with this?
Looks good.
So we have n factors. If choose k to give x, then rest n minus k give y. And this is why a and k is just n choose k's. We're choosing k factors to be x. We're really doing a little bit more than that. If there are n factors and we choose k to be x, how many factors remain? So if we choose k factors to be x, how many factors must be y?
N minus k.
N minus k. And so we really have n minus k factors left over. Of those n minus k factors, how many of them must we choose to be y?
N minus k.
N minus k. Oops. And so really what we're doing is we're multiplying by 1. But because this equals 1, we normally just ignore it and we normally just write that the coefficient in the binomial theorem is just n choose k. So this is the binomial theorem. X plus y to the n is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k, or the sum, k goes from 0 to n, n choose k, x to the n minus k, y to the n. Y to the k. So we drop the n minus k, choose n minus k because it's just 1. Okay. And again, when you drop terms that are 1, it's sometimes a little bit harder to follow what's going on. Why is it n choose k? It's really n choose k times n minus k choose n minus k. And this helps us, if we do probability, to extend to what's called a multinomial coefficient rather than a binomial coefficient. Amazingly, sometimes in life you have more than 2 options. So what would you do if you had 3 options, 4 options, 5 options? There are ways to generalize. And so you can teach an entire class on, combinatorics like this, on counting problems. But these are the basics. This is the most important counting relation. The binomial theorem is very important. One application is calculus. And let's say we want to calculate, let's say n is a positive integer, f of x equals x to the n. What is f prime of x? Well, it's the limit as h goes to 0 of f of x plus h minus f of x, I'm sorry, not sure why I'm putting that in the denominator, minus f of x over h. And so this quantity is one of the most important things you will see in calculus. This is f prime of x. And so this is the limit as h goes to 0 of x plus h to the n minus x to the n over h. Since n is a positive integer, we can use the binomial theorem. And we'll get x to the n plus n x to the n minus 1h plus n minus 1 over 2 x to the n minus 2h squared plus n choose 3 x to the n minus 3 h cubed plus dot 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 plus h to the n minus x to the n over h. So when you look at this expression, what happens in the numerator? What's one thing you notice?
X to the n cancels out.
Yeah, good. The x to the n's cancel. And what do you notice about everything else?
They have an h.
They all have an h. So this is then going to give you an nx to the n minus 1 plus h times crap. I'm not going to bother writing it out. What does that crap go to as h goes to 0? Doesn't matter. It's bounded. This is bounded crap. And so if I take the limit, I'm going to get nx to the n minus 1. All we really need, we only need x plus h to the n is x to the n plus n x to the n minus 1 h plus something nice times h squared. That from that point onward, it's nice and everything has at least an h squared. That's really all we need to calculate the derivative. But this is one of the great applications of the binomial theorem, which is coming from these combinatorial coefficients. If we want, what is the derivative of x to the 3/2 or x to the square root of 2, we can't just use what we have above. What we have above only works when we have a positive integer because we're using the binomial theorem to expand out x plus h to the n. If I give you x to the 3/2, it is still 3/2 x to the 3/2 minus 1. But the proof is very different. And this is one of the big things to be careful about, is when are you allowed to use a result? Okay, are there any other questions from binomial coefficients? Okay, I'm going to just finish and actually do the derivative of something like x to the 3/2. I know we have a couple of people who are thinking about being teachers here. This is just a great way to talk about how careful you need to be when you are writing things up. As well as, for those of you who are interested more in theory, just how easy it is to accidentally assume something. So let's say we have f of x is x to the m over n, m and n positive integers. We could let g of x be f of x. Anybody want to guess what might be a good power? What would be a good power to raise f of x to? So what quantities do we have in this problem so far? So what do we have in play?
X to the m over n.
So we have x, we have m, we have n, we have x to the m over n. What would be a good quantity, good power to raise f of x to?
Squared.
I'm sorry?
Squared.
Okay, why squared? What in this problem makes you think squared is a good thing to do? You might be right, but where are you seeing something that's telling you, let me do a square? So do you see a 2? Do you see a squaring anywhere?
No.
No. So I don't think squaring is a good thing to do. What would be good to raise f of x to? What do we have in this problem?
Raise it to the nth.
To the nth, right? We have m and n as the integers coming into play. So it's reasonable to try to raise f to something involving m, n, or both. And we see that if we raise it to the nth power, I'll put it in red to make it, really drive home. What do we get if we raise it to the nth power? We just get x to the m, which is a nice function. And so now we know g prime of x is going to be n f of x f prime of x by the power rule, or repeated product rule. And that's going to be mx to the m minus 1. And that's okay as it's a integer power. So we can use the previous result. We couldn't use the previous result because we had x to a rational, and this proof required x to be to an integer. So if we raise it to the nth power, now we have x to the m, which is x to an integer power. And so now we can take the derivative. Well, how do we take the derivative of f of x to the n? You could just come up with a repeated product rule, or maybe the power rule, which is a special case of the chain rule. And now we can solve for f prime of x. And we'll get f prime of x as m x to the m minus 1 divided by n f of x. Well, that's m over n x to the m minus 1. F of x is x to the this is f of x to the n. Sorry, I dropped the n over here. And f of x to the n would just be x to the m. Did I make a mistake?
Shouldn't be
isn't
n
Oh, sorry, it's
to
n
the
minus
x
1. It's n minus 1. It's n minus 1. There we go.
Okay.
Sorry, n minus 1. So we would have x over n to the n minus 1. Okay, so now we have to do some algebra. M over n, x to the m minus 1, and then down below, x to the m over n times, n minus 1, law of exponents, it's x to the m over n times n, x to the m over n times negative 1. I'm just trying to do it very slowly. That's going to be m over n, x to the m minus 1, and down below we'll have x to the m, x to the negative m over n. So that's m over n, x to the m, x to the negative 1, x to the m, and then the x to the negative m over n becomes an x to the m over n upstairs. Right? 1 over x to the negative 3 is just x to the 3. And now notice the x to the m's cancel, and when the dust settles, we get m over n, x to the m over n minus 1. This is just what we would expect to be true. There are other ways to prove this, but this is a good way to prove it. It allows us to use results we already know. If you want to find the derivative of x to the root 2, that's more complicated. And this is a nice way to just review basic algebra. So as a challenge, x to the square root of 2 is e to the root 2 natural log of x. And once you go past calculus, we always use log for the natural log in advanced mathematics. So x to the root 2 is the exponential of root 2 natural log of x, and use the chain rule. And that the derivative of the exponential function is the exponential function, and the derivative of the natural log function is the 1 over function. So leave that for you to think about. But what I want you to get out of this is that if you want to look at proving things, you always want to ask what conditions must be satisfied if I want to use a result. So, if I want to use the derivative of x to the n is nx to the n minus 1, what you probably did in your calculus class is you probably only did it when n was a positive integer. And the teacher just kind of was quiet and just said at some point, the derivative of x to the r is r x to the r minus 1. It's a little bit more work because the standard proof is assuming that we can use the binomial theorem. A lot of you, when you were doing the homework problems, we want to try to calculate what was, from the homework, what is 3 choose 5? It is 0, as cannot take 5 objects from 3 when order does not matter. What's the most objects you can take from 3 when order doesn't matter?
3.
3. So we know that this is not going to be possible. But if we want n choose k to equal n factorial over k factorial n minus k factorial, even if k is greater than n, then we would need 3 choose 5, which is 3 factorial over 5 factorial negative 2 factorial to equal 0, or 6 over 120 times negative 2 factorial to be 0. So the only way that could work is we need negative 2 factorial to be infinity. There's no finite number we can put in that's going to work. So initially the formula n choose k, n factorial over k factorial, n minus k factorial, only works if n and k are non-negative integers and n is at least as large as k. We can extend it, but if we want the extension to work, we have to put in the constraint that numbers like negative 2 factorial, negative 3 factorial, the only thing that makes sense is putting them in as infinity. I know some of you have done complex analysis. This would be essentially, putting in a function blowing up. Okay, we've got a few minutes left. Are there any other questions that people wanted to discuss?
It's possible I've completely hallucinated this, but did I read or see somewhere that we would be doing something with strong induction at some point?
We might. Strong induction and regular induction is basically the same. Sometimes in strong induction, you assume that not only is it true for n, but it's true for everything up to n. They're really equivalent.
Okay.
Because when you just run through the argument, it's going to be the same steps.
Okay.
Now, there is such a thing as transfinite induction, but we're not going to cover stuff like that. We're not going to be inducting across infinities.
Will we be using Fermat's little theorem at all?
Yes. And in fact, Fermat's little theorem becomes extremely important in trying to determine if a number is composite. And just for the record, Fermat has two very famous theorems that both are FLT, Fermat's last theorem and Fermat's little theorem. The notation I like to use is FLT for Fermat's little theorem and FLT for Fermat's last theorem.
Does that apply to like groups too? Like
So for Fermat's little theorem is actually a special case on the order of groups in Lagrange's theorem. Any other questions? Okay, so if people find that there's other topics as the semester progresses from previous math classes or just things that you're curious about, let me know and I'll either try to work them into the class or just meet with you one-on-one. But again, it's sometimes hard when you haven't used material in a while, to remember exactly what is there, why is it true, and so always happy to discuss using stuff like this. All right, let me try to quickly upload this.